Recording. Yeah. So today is the last lecture on DPMS problem solving. We'll discuss a few bits of transactions that we had left 2PL. I will give you a crash course today on 2PL. So spend some like 20-25 minutes to explain you about 2PL, and then we'll move to indexing. Right? Indexing is a very easy topic and very scoring. So even if you learn things today, it's actually good enough, and we'll also solve questions. So without further ado, let's start. I'll just first discuss the TOC question that was asked, and then we'll go to the actual lecture. Okay, so this was the question that was asked, right? I've just copied it verbatim as it is as it's sent. So see, the thing is, you have this is more like you have to reject few of the strings and try to find out if they are, so you have to see. So okay, so what I'm trying to say here is, what you have to do is look at the DFA. Okay, let's forget about the regular expressions that are given. Let's look at the DFA. Okay, I will give you some strings. You will have to tell me, first of all, is that string accepted by the DFA or not? Okay, is Vishnu, is the game clear? I'll give you a string. You will have to tell me, is the string accepted by the DFA or not? Okay, fine. Okay, first string is 0. Is 0 accepted by the finite automata? No. So this is one of the string that is not accepted by the finite automata. So by definition, it should not also be represented, or it should not be generated by a regular expression as well. Correct, Vishnu? Okay. Is there any option that generates 0 for you in here? Which option? B. So option B generates 0. So option B goes down the gutter. That is not the right answer. Okay. Okay. Second string. Can you tell me if 1, 0 is accepted by the finite automata? Yes. So if 1, 0 is accepted by the finite automata, that also means 1, 0 should be generated by the 3 regexes that are given. Agreed? Okay. Will the first option generate 1, 0? Will the first option generate 1, 0? How? How will you generate 1, 0? So what should I take for this star? 1? Right? I should take star 1 for this. And what do you want me to take? I should take this as 1 only, right? Because if I take 0, then it becomes epsilon and you can't generate 0. I will take this as 1. Okay. But it generates 1, 0, 1, 1. It doesn't generate 1, 0. I need 1, 0. Can it generate 1, 0? Understood why it cannot generate 1, 0? 1, 0, 1, 1 is okay. Okay. 1, 0 it can't generate. Okay. So can I say option A goes down the gutter? Okay. Good. Okay. Can 1, 0 be generated by option C? Yes. So we can hold it for now. Can 1, 0 be generated by option D? No, because if you take 1 here, you are generating 1, 1, 1, 0. You need 1, 0, right? So option D also goes down the gutter. Now can you see the answer? So what is the method I followed? See, first check for if 1 or 0 is accepted or not. Then extend the tree. Check 1, 0, check 1, 1. Extend the tree. Check 0, 1, check 0, 0. As soon as you get one answer, just tick it and move ahead. If you don't, definitely you will get till here. If you do this only, right, you will get the answer. Okay, even Gate knows that. Even Gate knows that you have time limits. So you cannot actually do for every string. So, but in case they want to what shall I say? That word in Hindi we call pareshan. English mein, whatever it is in English. So it means if they want to, let's say, scare you or want to play with you, then you will also have to extend this further. You will have to look at 100, 101, then you have to look at 110, 111, but that's rarely the case. But do you understand the method of how to solve this question? Okay, perfect. Okay, can I proceed, right? It's okay, right? Okay. Let's go to the next actual lecture. Sorry. Okay. Yeah. So what I was saying is, let's go to the actual lecture. I'll first give you a quick crash course on 2PL. Okay. Okay. So I'll take only 30 minutes. Okay. Not more than that because we have things to cover. Okay. Let's say there are two transactions, T1 and T2. They are both executing concurrently. Okay. Let's say T1 wants to write the value of A. Let's say I will not write so generically. Let's say I want to write T1 wants to write the value of A as 1. Okay. Let's say T2 wants to read the value of A. Okay. This is the situation. Let's say the initial value of A is 0. What is the value read by T2? Always 1. Can it never be 0? Yeah. I will give you a hint. Both the transactions are executing concurrently. Both are executing parallelly. It could so happen that T2 gets to execute this instruction first, then T1. In that case, T2 will read the value of A as 0 or 1. It could be either 0 or 1 because both are executing concurrently. Okay? Is it fine? Now you don't want this to happen. You obviously don't want things to work like this. So what you do is you do some synchronization. Have you learned operating system? Semaphore, right? You know semaphore. So semaphore or mutexes. So what I will do is I will say before T1 wants to write to this data item, please obtain a lock on it. And then after you have done the writing part, you unlock it so that when T2 wants to read it, it will read only the value 1. Okay. Okay. Now, here is the thing. Uh, Maybe this is not a very good example because T2 may also lock it first and read the value of 0. But let's say T2 also wants to write the value of A as 2. Right? Let's say this is the example. So either the value of A will be written as 2 when T2 gets a lock first, or T2 gets a lock next, or if T1 gets a lock first, it will write the value of A as 1, and then T2 gets a lock and it will write the value of A as 2. So you need some locking mechanism to have some deterministic behavior between transactions and to prevent race conditions. So what you do is, sorry, so a transaction can either acquire something called a shared lock or an exclusive lock. Does anyone know here what is a shared lock? When will the transaction acquire a shared lock? If the transaction wants to read, and if a transaction wants to write, it will acquire an exclusive lock. Okay, and if there are multiple transactions and they only want to read a value, can they do so simultaneously? Yes, because it's a shared lock. Shared lock, if a transaction holds on to a shared lock, the other transactions can also acquire a shared lock as well. Because you're trying to read the data only, there is no race condition involved between two read operations. Okay, so this is what is called the compatibility matrix. It's like if a transaction has a shared lock, okay, it can acquire another transaction can also acquire a shared lock. It's fine. But if a transaction has a shared lock, another transaction cannot acquire an exclusive lock. If a transaction has an exclusive lock, other transaction cannot acquire a shared lock, cannot acquire an exclusive lock. So this is also called the compatibility matrix. Okay. Okay. Now the problem here is that, for example, if you consider a situation like this, for example, if I have T1, if I have T2, okay, and let's say there is something called you acquire a lock, okay, let's say it's a shared it's a shared lock. You read the value of A and then you unlock it, okay, and then afterwards, let's say you acquire a exclusive lock on A, you write to the value of A, and then you unlock A. Let's say now again what you do is you acquire a shared lock on A, you read the value of A, and then you unlock A. Now, is this schedule conflict serializable? No, right? Because conflict serializability means if there are two transactions T1, T2, since this is a conflicting operation, so there is an edge from T1 to T2, even this is a conflicting operation, so there is an edge from T2 to T1. Okay? And there are some schedules, if you just follow locking, they will not be even serializable. What is the meaning of not being conflict serializable and not being serializable? Not being serializable means it is neither conflict serializable or what is the other type of serializability? You guys know? We discussed in the last class. View serializability. So it is not serializable mean it is not view serializable, neither conflict serializable. So what we do is we do something called two-phase locking. What is a two-phase locking? Two-phase locking, there are two phases. One is called the growing phase. Then there is something called a lock point. And then we have a shrinking phase. What is meant by all this? We'll tell. It's simple. It's just technical jargon. So growing phase is a phase when when the transaction can acquire locks. Growing phase is the phase when any transaction can acquire locks. Okay. Okay. Now, shrinking phase is a phase where the transaction can release locks and release locks. It's not that transaction can actually, whenever it wants to, will acquire a lock and release a lock. Transaction will only acquire locks in the growing phase. It cannot unlock. For example, if there's a transaction T1, if it acquires a lock on A, and then if it acquires a lock on B, suppose it unlocks A, then I can't acquire a lock on C. This is not allowed. You can only acquire locks in a direction, in a phase. So that's a growing phase. And then once you start unlocking the data items, you cannot go any further. Okay, you can only unlock this point where there is this junction, which is you exit the growing phase and then go to the shrinking phase, is called a lock point. Okay, so far so good. People who know this can be also happy they are able to revise. Who don't know also may be able to understand by now. This is nothing very rocket science. Okay, so growing phase is a phase when transactions can acquire locks. Shrinking phase is a phase when transaction can release locks. Release meaning unlock. Okay, and the point where the growing phase ends and the shrinking phase starts is called a lock. Okay, so now there are theorems, there are proofs as well. I don't want to go into all that now. It will take a class actually. There are some points I will write you here which will help you in your exam. Please keep them as short notes. 2PL always generates conflict serializable schedule. There is a gate question. I will go to that later. Always generates a conflict serializable schedule. Please keep this in mind. Okay, that's always the case. 2PL always generates a conflict serializable schedule. Okay, and 2PL may generate irrecoverable or cascadeless schedule. Now, what is cascadeless? I will tell you. Irrecoverable, we already looked at it in the last class. So, may generate irrecoverable or cascadeless schedule. Okay. So, what happens here is, see, before I go any further, let's say I have two transactions T1 and T2. Let's say three transactions T1, T2, T3. Let's say four transactions T1, T2, T3, T4. Let's say T1 acquires a exclusive lock on A. It changes the value of A to 1 and then it unlocks A. Okay. Let's say T2 acquires an exclusive lock on A, makes it 2, unlocks A. Let's say T3 acquires an exclusive lock on A, makes A as 3, and then unlocks A. Okay. And then T4 acquires an exclusive lock on A, acquires the changes it to 4, and then unlocks A. Okay. First of all, is this allowed in 2PL? How many of you say yes? How many of you say no? Is this allowed in 2PL? Which means, is the growing phase and shrinking phase applicable here? Can you see this violated by somehow? It's allowed. Okay, don't consider that there is an unlock here and lock here, so it's not. No. Okay, what I mean is, I wrote TX here, then I wrote the same TX here. I'm not writing TY. Okay, so it's absolutely okay. For a given transaction, this is the growing phase, this is the shrinking phase. This is the growing phase, this is the shrinking phase. This is the growing phase, this is the shrinking phase. This is the growing phase, this is the shrinking phase. Clear, everyone? You acquire the lock, we are in the growing phase. You release the lock, you are in the shrinking phase. Okay. Is there a conflicting operation between all these transactions? It's clearly visible, right? It is. I mean, this is a right, this is a right, this is a right. All four are conflicting operations. You guys agree to this? There's a dependency from T1 to T2, T2 to T3, T3 to T4. Suppose I abort T1. Okay. There's some problem happened and T1 has to abort. So you will roll back the change given by T1. Now, was there a dependence? So, for example, if you are not able to see the dependence, let's say this 2 was actually A equal to A plus 1. Okay, in an exclusive lock, I can also read the value of A. So A equal to A plus 1. If you abort this transaction, that means you are changing the value of A back to what it was earlier, which is, let's say, 0. Now, since this transaction T2 was a dependent on T1, T2 has to roll back. Now, since T3 was dependent on T2, T3 has to roll back. Now, since T4 was dependent on T3, T4 has to roll back. Can you guys see this? Because of T1, T2 had to abort. Because of T2, T3 had to abort. Because of T3, T4 had to roll back. So this is called cascading rollback. It's called cascading rollback. Sorry, not cascadeless schedule. The problem with 2PL is it can generate cascading rollbacks. And you saw an example just now. Okay. And when will you generate an irrecoverable schedule? Let's say that T2 commits here. Okay. And T1 does not commit. T1, let's say, aborts here. Okay. T2 has committed, job T2 is finished, job of T2 is finished. When you abort this transaction, you will not be able to roll back this easily. You will have to look at the logs and all. That's a pain because you have committed the transaction. So we call it irrecoverable. So you cannot recover from the inconsistency. So 2PL can also generate a irrecoverable schedule. Okay, so far so good. So far so good, everyone. Only Vishnu is answering, and others all good. Jigya, Mohammed, Rohit, all good. Okay. Now, as you see, there are some types of 2PL, and the types of 2PL try to minimize some uh, problems that are observed in basic 2PL. So this is called basic 2PL. There are some types of 2PL that minimizes these problems. For example, let's say, let's test your OS knowledge today. Let's say there are two transactions, T1 and T2. Let's say T1 has a lock on A, T2 has a lock on B. Okay. Let's say T1 wants to get a shared lock on B. Let's say T2 wants to get a shared lock on A. Okay. And let's say they do some job, and then they unlock A, they unlock B, T2 unlocks A, T2 unlocks B. My first question, are they following the 2PL rule? Is there a growing phase and shrinking phase? Yes. What is the behavior of this transaction? Let's say the sequence of operations occurred like this. First, T1 executed lock of X, then T2 executed this, then T1, then T2. What is the behavior? What do you think will be the behavior of the transaction? So T1 gets a lock on A, correct? T2 then gets a lock on B. Now T1 wants to get a lock on B. Will T1 get the lock on B? No. T1 won't get the lock on B. T2 wants to get the lock on A. Can T2 get the lock on A? No. So what is this situation called in operating system if you have learnt? Deadlock. Deadlock, right? You are waiting for T1 is waiting for T2, T2 is waiting for T1. This is called deadlock. So can I say 2PL can generate a deadlock transaction? Can lead to deadlock? Very good. So this is the third point. 2PL can lead to deadlock. Everyone understood, right? Why deadlock can happen? Right? And we used a very, very simple example. So let's say I want to tackle this problem first. I want to avoid deadlocks and use 2PL. Okay, I want to avoid deadlocks and use 2PL. So what I will try to do is just before the transaction starts executing, I will ask the transaction, boss, what data items do you need a lock on? And the transaction T1 will say, boss, I need an exclusive lock on A, shared lock on B. T2 will say, I need an exclusive lock on B, shared lock on A. So what will happen is just before the transaction starts. So just before the transaction starts, you will give the lock. Just before TX starts, you will give you as in the computer, okay, the database management system, no software, will um, provide, or the transaction will acquire all the locks that are required for all the data items that the transaction is requesting for. And if someone, let's say T1 first asked, and T1 will get the lock on A as well as B. If T2 asks, T2 will have to wait until T1 finishes. Once T1 finishes, unlocks A and B, then T2 will get the lock. Okay. So in this case, what will happen here is you will actually not have any growing phase, because just before the transaction starts, you are providing all the locks. There will only be a shrinking phase. Now, can you tell me whether there will be a deadlock occurring if this is the rule that we are following? Can there be a deadlock just before the transaction is starting? So in your operating system, you may have learned something called deadlock prevention or deadlock avoidance strategies. There are 4 conditions why deadlock can happen if you remember your operating system. One is, I think, preemption. Another is no preemption. Another is hold and wait, circular hold and wait. So how do you solve hold and wait problem of deadlock? You first ask the process, boss, what are the locks you need? What are the semaphores you need? The process says, these are the semaphore I need, and then only you get to execute the process. Do you guys remember this, right? This is not Latin, right, for you? I have not taught you OS, but I assume the professor may have taught you the lecture. So may have taught you semaphores. So just before the transaction starts, if T1 gets all the locks, then it's fine. There won't be any deadlock. But what is the disadvantage of this approach? Can you think of a disadvantage? Let me give you a hint. Suppose, okay, suppose T2 wanted to work on, let's say, C. Okay, let's say T2 wanted to work on, let's say T2 after acquiring a lock on C, it writes some value to C. Okay, and then T2 wants to get a lock on A. Okay, let's say T1 got the lock first. I mean, T1 got the locks A and B. Will T2 be given any lock? Will T2 be given any lock? Yes. Hello, can you hear me? Am I audible? Yeah, right. Okay. So T2 wanted to work on which data item first? Was it A, B, or C? C. So is there a problem? Let's say T1 wants to work on A and B first, so it wants to acquire a lock. T2 only wanted to work on C first. But just because you said that before T1 starts, you will give the lock A and B, and T2 also wants a lock to A and C, you will tell T2 to wait unnecessarily. T2 could have gotten the lock to C and done the operation, right, of C, right? So that is the disadvantage. The disadvantage is lesser concurrency. Okay, this type of 2PL is called conservative 2PL. Okay, clear conservative 2PL? Okay. Now let's look at the other problem. The other problem was cascading rollbacks, right? Cascading rollback is a problem, right? If the transaction aborts here, T1 aborts here, you have to roll back T1. Because of it, you have to roll back T2. Because of it, you have to roll back T3. Because of it, you have to roll back T4, right? It's a problem. How do I tackle this problem? Let's say what I say. Let's say what I say here is. 1 second. Yeah. So let's say that T1, if it acquired a lock on A, it will keep on holding the lock to it until and unless it commits. All locks will be held by a transaction until and unless it commits. So let's say T2 is there. It will take a lock on X, write the value A to A plus 1, and then commit. And then let's say T3 gets a lock on X. And the rule I say here is once the transaction commits, all the locks will be released. Understood? Understood the situation? The situation is if a transaction can acquire a lock, but it will acquire all the locks until the transaction commits. Okay, it will keep on holding all the locks till the transaction commits. So once the transaction is committed, the lock will be released. Now, once a transaction is committed, can the transaction go to an abort state? You may have seen a diagram, right? I didn't show you that diagram. There is a diagram in transaction where you say the transaction has started, there's a state diagram, right? Once the transaction commits, it can never abort. Either the transaction will abort or the transaction will commit. Commit meaning it has done its job, everything is okay, it will save the results to your database. Now, in this case, there will never be a cascading rollback. You are free from cascading rollback. So, what are the points? All locks are held until the transaction commits. Second point is it generates cascadeless schedule. You will never have cascading rollback here. Okay. Okay. Now, it only consists of growing phase. If you see, there is no shrinking phase here. You are not unlocking anything directly. You are using the commit operation to unlock things. So there is no unlock you are doing here. So it consists of only growing phase. Now, what is the problem with this? Can you tell me what is the behavior if this happens? What will happen if this is the situation? All locks are held till the transaction commits. So let's say T1 acquires a lock on A, exclusive lock on A, and then a shared lock on B. T2 acquires an exclusive lock on B, then a shared lock on A. What is the behavior of the system if this is the situation? Yes. What is the behavior of the situation? What is the behavior if this is the situation? Yes. Come on, it's easy. We already looked into it. Deadlock, right? It's a deadlock. So can we say that this type of 2PL suffers from deadlocks? Can we say this statement? Okay, good. Suffers from deadlock. So this type of 2PL is called rigorous 2PL. Okay. Now tell me one thing. Suppose all the transactions are only using shared locks. Okay. For example, let's say this is a situation. Uh, okay. There will be a question now. Okay. Okay. Let's say I will just explain you like that. So suppose all the transactions are want only shared locks. Okay. They only want shared locks. They're not concerned with exclusive locks. Is that a problem in the database system? Can two transactions acquire shared lock on a single data item? come on, there's a shared lock held by transaction T1. Someone else wants a shared lock. Will he get or not? Will the transaction get or not? There is no problem if there are shared locks, right? Rigorous 2PL says all the locks are to be held until the transaction commits. The point is, why do you want to do that? Let's say you want to relax it for shared locks. You want to say you can have a shrinking phase where you can only relax, you can only release the shared locks. You cannot release the exclusive locks. Understood? Let's say there are only shared locks. Is that a problem? No. Then why do you want to give a restriction on shared locks? Rigorous 2PL says, boss, all locks are to be held until the transaction commits. Why? If there is a shared lock, what is the problem? I can hold a shared lock if I want to. So, rigorous 2PL with a relaxation that you can release the shared locks. Plus, shared locks can be released is called strict 2PL. Is called strict 2PL. Okay. Is it clear, everyone? The three types of 2PL? I tried to give a small crash course. Exactly half an hour I took. 8:56 I started. Now it's 9:26. So is it clear? Any doubts regarding any of the 2PL types? Can we go to the questions quickly? Okay, perfect. Perfect. Let's go to the questions. Okay. This I think we already looked at, right? Did we look in this question? I think we did. No? Okay. So here is the thing. So the thing is, okay, perfect. So what did I say? 2PL generates what? 2PL generates what? Conflict. Sorry, I told the answer. Sorry, I told the answer. Sorry. I wanted to say dash serializable. I told conflict dash. Okay. Yeah. So 2PL generates conflict serializable schedules. Is this schedule conflict serializable? No. So does it follow the scheme of 2PL? No. So it cannot occur in a scheme using 2PL because it is not conflict serializable. Can I declaratively say that it is not serializable? Can I say that it is not serializable? I have to check for which there's another serializability called view serializable. Is there a blind write? Can you see any blind write in the transaction schedule? I see a read B, then a write B. I see a read A, then a write A. I see a read A and a write A. I see a read B and a write B. There is no write operation without a read operation. So there is no blind write. Now, can I say option D is the correct answer? Clear, everyone? Schedule cannot occur in a scheme because it is not conflict serializable. Schedule is not serializable because it is not even view serializable. Okay, clear? Can I proceed? Okay. Which of the following statements about 2PL is or are true? This is GATE 2024. Achha, I have to give you one more thing. So here is the thing. So if a schedule is 2PL, oh, I think I had given you, right? So every conflict serializable schedule is view serializable. I think I told you this, right? I drew a Venn diagram. Okay, fine. Can you answer? Is option A correct? If a schedule is in 2PL, the schedule is what? Conflict serializable. And what did I say in the last class? Every conflict serializable is also view serializable. Remember this thing? I drew a diagram like conflict serializable subset and view serializable is the superset. Remember this? Okay. So if I say if it is conflict serializable, it is view serializable, then 2PL is also serializable, I can say, because it is both conflict serializable and view serializable. Option A is correct. How about option B? Is option B correct? No. No. What option B says, you can acquire a lock on A, write A equal to 1, then unlock A, then you can acquire a lock on B, write on B, and then unlock B. Is this allowed in 2PL? Option B is incorrect. Is option C correct? In 2PL, once you have released a lock, can you acquire any lock? Once you release a lock, you are in the shrinking phase and you cannot go in the growing phase now. So C is true. Is D true? Deadlock is possible with 2PL. We just saw the example. So what is answer? A, C, D are true. Okay. Fine. Okay. So these were actually, there are some more questions as well on 2PL. They are almost the same as what I taught till now. Okay. They are no different. There was a, one second, there was a, I think I didn't, I think there was a question on strict 2PL which I didn't put here, is it? I think I put, one second, let me just check. An important question. Hmm. Okay. No. Okay. No, no, okay. It was this question only. Okay. Let's see. Why am I not able to find? Uh, yeah. So it's a big question. I will just write a few things. Okay. Now, what they are asking is they are asking you that. So I'll write it here. Okay. So what they are asking is they are asking you that which of the following schedules are allowed by strict 2PL. Okay. Which of the following schedules are allowed by strict 2PL? Okay. Then they run on a schedule that supports a shared lock and an exclusive lock. There are shared lock, exclusive lock. I'm not writing that. That is simple, I guess. So the option A is there are two transactions, T1 and T2. You first acquire a shared lock on A, then you read from A, then you acquired a shared lock on B, then you read from B, then you acquire an exclusive lock on B, then you write to B, sorry, exclusive lock is acquired by T1. So you acquire an exclusive lock on B, then you write to B, then you unlock B. Okay. Now, with this only, is it enough to say it's not following strict 2PL? Is there an exclusive lock that you are releasing that you are not supposed to release? You can only release shared locks in strict 2PL, right? You remember this point, right? This is an exclusive lock on P. You're trying to unlock it. That is not allowed, sir. You have to commit the transaction if you have to remove exclusive locks. So option A becomes untrue. There are some more here, but I'm not writing that. But I hope it's clear by now. Option B is like this. So there is T1, there is T2. You first acquire a shared lock on A, then you read A, then you acquire a shared lock on B, then you read B, then you acquire an exclusive lock on B, you write to B, then you unlock A, then you commit. Okay, then you take an exclusive lock of C, you write to C, you unlock B, you commit T2. Is this following strict 2PL? Look at the unlocks. Okay, look at the unlocks. There is an unlock here, right? There is an unlock here. Are you unlocking a shared lock or an exclusive lock? You are unlocking a shared lock. That is allowed. Are you unlocking an exclusive lock or a shared lock? In T2. No, it's a shared only, right? See, unlock of A. What is A? You have acquired a shared lock on A. Unlock of B. How have you locked B? You have locked as a shared lock on B. Clear, Vishnu? Yeah. And there was one nota and there is one more option which you can see later. But okay, so this is the funda of strict 2PL. There was given a schedule. I think I had put this. I don't know why. ठीक है चलो छोड़ो never mind. Okay, so there is one more concept about concurrency control called timestamp ordering. I am really very doubtful there will be time for that. Okay, also there are not much questions also asked for it. So I will suggest you to, if you have any doubts, any question that you are not able to solve or understand, let me know. I'll give you support on it offline. Okay, don't worry. I'll give you support on it offline if you have any questions on it. Okay, there's one more thing, but just letting you know that I'm leaving it because there's shortage of time. Okay. Okay, so okay, now let's go to indexing. It's an easy topic. It's not very difficult. Uh, how many of you here have studied indexing? No one? Okay, that's a good answer. So, okay, that's fine. That's fine. That's fine. We learn it today. It's simple. Okay, we learn it. Okay. Okay. So, okay. So you have seen a database, right? A database. I'll use some terminology here. Okay. A database is typically stored as a file. Okay. If you have used MySQL, then you have seen the database has been stored as a file, right? You guys might have seen it. Now, a database file contains some set of records. Okay. Let's say there is a student database. A student database consists of some set of records. And let's say the student database, this is the file, there are some set of rows here stored. These are the different records of a student. His roll number, ID, name, subject, age, whatever it is, they are stored one by one in these columns. Okay, and each of these rows is called a record. Okay, so far so good. So far so good. Database file consists of a set of records. Now, these records are grouped into blocks. And the blocks are stored in the database. It's like, let's say, for example, I'm just giving you an example, okay? This record here, let's say, takes 100 bytes. of space. If you want to store a record, it takes 100 bytes. Now let's say that the database consists of blocks and each size of a block is 1000 bytes, which means in a block you can store 1000 bytes. Can you tell me how many records you can store in a block? Each record has 100 bytes. The block size is 1000 bytes. Can you tell me how many records you can store in a block? 10, right? You can store 10 records in a block, right? So is the organization clear? Database stored as a file. File contains set of records. Records are grouped into blocks, and the blocks are stored in the database. Is it clear so far? Okay, perfect. Now, if I tell you this is the database, you want to search for a record. You want to search for any record. Let's say there is a database that consists of there's a database. Let's say this database consists of 1 million records. 1 million is like 10 lakhs. Okay. Let's say these database records are not sorted. Okay. For example, you know that ID is unique for every student. Every student has a unique ID number. And let's say these records are not sorted based on your ID. They are just randomly records are written like that. Can you tell me what is the time complexity if I want to search for a record here? How much time it will take? Which algorithm will I use to search for a record? There are two algorithms you have learned. One is called binary search, one is called linear search. What is the algorithm that I will use to search for a record? Given that the data is unsorted. Yes? Come on, if you don't answer this, it's a very big problem. You will use a linear search because data is not sorted. So what is the time complexity to do a linear search? Order of n. So is binary search more faster or linear search? Binary search. Okay, because binary search ka time complexity is what? Log n. Now what I do here is, I will collect all this ID and I will store it in another file. I'll just store the ID and I will also store the something we call block pointer, a pointer to the block where the data with ID is present. And let's say this ID is sorted. This one, once I am trying to push things in this index, okay, this is also called a index file, and I'm trying to push the IDs here, and I'm trying to ensure that the IDs that I push here, they are sorted. I can use something called insertion sort to do that. Or I can use any type of sorting algorithm to actually do in-place sorting. Okay, in-place sorting algorithm is insertion sort, if you know. It's an online sorting algorithm they call. Why? Because as you are placing the data inside the index file, I will make sure I'm storing them in a sorted order. Is it clear so far? See, I'm not very good in DSA, okay, but still I'm trying to explain you as much as I can. So please give me feedback if it is not clear, okay? So these are ID, and each of the ID contains pointer to the block which is there in the database, okay? Now, can you tell me, since this index file is sorted, can you tell me how much time it will take to search for a record? order of login, because you can use something called binary search. Order of login because you can use something called binary search. Can everyone see that? Is everyone fine with this argument? Okay. Now you might argue saying, boss, okay, I understood this. Now you can search for a record. It will take order of login. Awesome. Okay. Let's say, actually it will take order of login plus 1. Why? Can you tell me why? Because index file is giving you the record, or it is giving you the pointer to the record where you have to go. What is the index file giving you? The record or the pointer to the record? It's giving you a pointer to the record, right? You are not getting the record itself. You have to actually do one more access to get the corresponding record, the entire set of rows, the entire row that you need. So it's order of login plus 1. Everyone agreed? This is a great question. Later we'll solve. Okay, they have asked this. Okay, so now let's come back to the major thing. You might say, boss, okay, let's say this data was sorted. Then I don't need indexing because I can simply apply binary search here. And if I apply binary search here, I will get the record. Right? You might think this. I mean, it's very natural to think. I said this ID is unsorted. You're just basically trying to store the ID somewhere where you make it sorted such that your search time is reduced. So if the data is sorted, you don't need indexing, right? No, that's not the idea. See, what did I tell you? The record size is 100 bytes. Okay? The block size is 1000 bytes. And you're storing things as blocks in the database for faster access and all. Will the index file also contain 100 bytes in every row? Will this also be 100 bytes? What do you think? Am I storing the entire record in the index? So will it be 100 bytes? It will be very less, right? It will be very less. Pointer takes only 4 bytes in C. And let's say this ID takes about 5 bytes. Let's say 6 bytes, okay, just to make it a whole number, 6 bytes. So this index record can be stored in 10 bytes. Do you agree? Now, how many records of the index can you store in a block? Suppose the block size is 1000 bytes. How many records you can store in a block for the index file? Will it be still 10 or something else? Each record of the index file takes only 10 bytes. The block size is 1000 bytes. How many records of the index file can you store in a block? 100 records. Is it more or less than the earlier case? It's more. Obviously more. And you can, and if you store things in a block, as much as you like, as much as you can store, the better. So even if the data is sorted, you will see this later also when we do numericals. Okay, we'll see this later. If the data is sorted, then what happens is you will get more records in the index file that you can store per block. And that's why it's always beneficial to do indexing. And this is called indexing. Okay, is it clear, everyone? And just to give you some more technical jargon, okay, I don't like to give, but I have to give because at one point you have to. Block pointer should be clear. It points to the block where the data is present. And the ID is also called the anchor attribute. The attribute that you are using for the index is called the anchor attribute. Don't be scared if someone says anchor attribute. It's nothing but the column that you have chosen from the record to act as your index key is called the anchor attribute. Okay? Okay? So far so good? Okay. Now let's say that the database is like this. So the database has records like this. So Oh, sorry, earphones fell. Sorry. So the database has records like this. There is roll number 1, there is roll number 2, there is roll number 3. Okay. There, and let's say you go a bit down, there is roll number 11. You go a bit down, there is roll number 21. You go a bit down, there is roll number 31. And let's say that each block contains 10 records. So this is one block, this is one block, and this is one block. Okay, let's say each block contains 10 records, B1, B2, B3, and so on. Okay, let's say I give you one index file where the search key is, let's say this is the ID attribute, the search key is the ID attribute, and the block pointer points to the block which contains the ID. So let's say there is an ID 1, the block should be this. Let's say the ID is 2, the block should be the same. ID is 3, block should be the same. ID is 4, block should be the same, and so on and so forth. Can I also do something like this? For example, let's say I tell you that, boss, the problem is not actually with things inside a block, because inside a block there is only 10 records. It won't take you very long to search for a record inside a block, right? It won't take you much long. Come on, like inside a block you can do even linear search, only 10 records are there. It's very less. So I will store the record to the first key. Then I will store the record for the second block, first key. Then I will store the record for the third block, first key, and so on and so forth. Now, if someone wants to search for a record of ID 2, he will look at 1, he will see the next one is large, it is more than 2, so it will go inside the block 1 and then search for the record 2. And it can do so because the index file, the ID is sorted. Since the ID is sorted, it knows that this ID2 will only be present in the block that contains ID1. It won't be present in the block that starts with ID11. Okay, nothing sound Hebrew Latin to you? Everything so far so good, right? Nothing is sounding Hebrew Latin? Okay. Now, for the benefit of the size of the index file, can you say if this is better or the earlier one? See, the earlier case where you were storing a block pointer for each ID, you were still storing the block pointer. You have to go inside the block and search for ID. Now you don't have to do that. Now also you have to do that, but can I say that the index file is now smaller because you are not storing the block pointer for every ID? Can I say this? So am I storing a block? Am I storing a block pointer for each ID? No, this is called sparse index. This is called sparse index, where every search key, the anchor attribute is also called the search key. Okay, the search key does not contain block pointer for every record, and this is very maybe block pointer for every record. This is called sparse index, and if you store the search key for every record, it is called dense index. Dense index is you store the block pointer for every record. Sparse index is you store the index in the index file, you store the block pointer not for every record, maybe for the first record of each block. Okay, is it clear? Sparse index and dense index. Can I proceed? Any questions so far? No questions? No questions till now? All good? Okay, perfect. All good right now? Perfect. Now, can I use a sparse index for an unsorted file? Can I use sparse index for an unsorted file? No. Please don't answer me for maybe for helping. Please let me know if you actually understood it. Will you need, can you store, if a data file is not sorted, can you store a sparse index for it? For example, if this data file is not sorted, 2 could be a record that is present here, right? In the last row. 2 could be a record that is present in the last row. So can you say that after 1, in this 1, there is the 2 is present? In this case, it is. Let's say I remove it. Okay, let's say I store the 2 in the last row. So in the block that contains 1, the 2 does not contain here. For example, this might be 32. So if a file is unsorted, you can never store it as a sparse index. Please keep this in mind. You will always have to resort to dense index. Okay, so let's move ahead. Okay. Now there are some types of indexing in the way how you try to search, how do you try to select the anchor attribute and how you try to uh, do the indexing. So the first type of indexing is called primary indexing. Primary indexing. What is primary indexing is that it is assumed that the main file is sorted. Now, if the main file is sorted, what type of indexing I can do? Sparse or dense? What type of indexing can I do? Sparse or dense? Sparse indexing I can do. Very good, very good. Sparse indexing is an example of sparse indexing. But what is the main feature of primary indexing? Why is it called primary? Is that your anchor attribute is the primary key of the table. Whatever is the primary key of the table becomes your anchor attribute. Okay. Now, how many number of entries will be there in the index file? Can you try to answer? Any guess? The answer could be either number of blocks or a number of records. What do you think? How many entries will be there in the index file? Let's call it small n. Are you storing an entry for each record? Are you storing an entry for each record? No, right? You just said sparse indexing, so you're not storing an entry for each record. You are storing an entry for each block. You are storing the entry for each block. So how many number of entries will be there in the index file? The number of blocks in the main file. Okay, so far so good. Okay, now can you answer in terms of n, how many number of accesses do I require to access a block using the index file? Can I use binary search is the first question you should ask. If I can use binary search, then what is the time complexity? So how many number of accesses you need to do in order to access a block in the using the index file? I am not saying how many number of accesses do you need to access the index file. I am saying how many number of accesses you need to access a block in the index file. So you need log base 2 of n to search for the index in the index, search for the record in the index file. Is this enough? What do you get by the index file? You get the record or you get the pointer? You get the record or you get the block pointer? You get the block pointer. So you need one more access to actually retrieve the block. Okay? Is it clear? Everyone, Vishnu, Jigya, Mohammed, Rohit, everyone okay? Nothing Latin till now? Please let me know if anything sounds Latin, okay? Okay. The second type of indexing is also called as clustered indexing. And what it means is, let me explain you with an example. So clustered indexing is like this. Do I have another slide? Yes, perfect. So clustered indexing is, the assumption is again the main file is sorted. Others I will write a bit later. Let me first explain you what it is. So main file is sorted. Okay. Let's say there is an attribute of a database, capital A, and the data is stored like this. It is stored like this. It's stored in the sorted order based on the capital A. It's sorted on capital A, and it's stored like this: 1, 1, 1, 2, 2, and then let's say 3. Now, can you tell me if can A be the primary key? Can A be the primary key? No. Why? Because A contains duplicates. Primary key mein you're not allowed to put duplicates. Correct? So in the index file, let's say I store this like this. So for each value, I will have a entry, and the block pointer will point to this block containing the value with ones. Similarly, there will be another entry for capital for 2, where maybe if you just don't want to even store the block pointer, you can store the record pointer for the first record. And then you store the record pointer of the record with first value as 2. For 3, you store the record pointer with the first value as 3. And let's say you want to search for a given record. So 1 is present, so you will retrieve these 3 rows. And within these 3 rows, you can actually do the searching. Let's say there will be another capital B, which will help you to distinguish between which row you want among those 3 rows. But at least you can search like this as well. You can search for, so for every record, I do not have a index associated with it. But for every record search key value, I have an index associated with it. Does it make sense? For every record value of the anchor attribute, I have a search key associated with it. So here the anchor attribute is a non-key attribute, something which is not a key attribute. It's a non-key attribute. Now, will you call it sparse indexing or dense indexing? Are you storing an index for every record? Are you storing an index for every record? So if I say you the definition, that's where it matters. If I say that you are storing the index for every record, it is called a dense indexing. If I say if I tell you I am storing an index for every record value for the search key, you understand what I say? The difference between these two? One statement is I store an index for every record. Am I storing an index for every record? Have I stored an index for this record? The second one with A as well. Have I stored an index for this record? Have I stored an index for this record? I am only storing the index for the first record with value 1. I'm not storing an index for the other two records which has value 1. So this you can say is a sparse indexing as well. But if in the question they say that in clustered indexing you store an index for each record value, what will you answer then? Suppose in the question it says, give me either whether it is true or false. The statement is, for every value of the anchor attribute, you are storing an index record. What will you answer? Is it true or false? For every value, I am storing the record, index pointer. For every value, I am storing the index record. Let me repeat the thing. For every value, I am storing the index record. I'm not saying for every record, I'm storing the index value. I'm saying for every value, I'm storing the index value. So is there an index record for value 1? Is there an index record for value 2? Is there an index record for value 3? Jigya, since you answered false. So it depends on how the question is given. Don't just blindly say it is a sparse indexing. It can also be called dense indexing. It depends on the context, what the question is saying. If the question is saying you're storing an index for every record, that is false. If you're saying if it's storing an index for every record value, that is true. It depends on how you say it. Okay, so please keep that in mind. Again, if you don't understand it, don't worry. Till now, Gate has only considered clustered indexing as sparse indexing, but tomorrow you don't know what can happen. So in this way also you are storing the uh, index as a sorted file, and the number of entries in the index file will be the unique values that are there in the anchor attribute. Number of entries is the number of unique values that are present. The number of unique values that are present. Okay. Now time for some technical jargon. And maybe I should keep the technical jargon for the next one. Okay. So in all of these cases, both of these cases, what is the common part in primary index and cluster index? What is the common part? What is the common thing? I am assuming the file is sorted. Suppose the file is not sorted. Then what type of indexing you will have to do? Sparse or dense? Sparse or dense? Dense indexing. You have to store an index for every record. So this is dense indexing. And since you have to store an index for every record, how many number of entries will be there in uh, this? How many entries will be there in the index file? Will it be the number of blocks or number of records? Number of records. Okay. And this type of indexing is also called as secondary indexing. Okay, clear everyone? All three types of indexing? Any questions? Vishnu, Jigya, Mohammed, Rohit, all clear? Three types of indexing? Okay. See, I'm trying to make sure that I'm also on time. So if you still have any questions, I'm always available on WhatsApp. Don't worry. So, but anyways, okay. Till now, I think it's clear. Okay. Now there are some technical jargons which are associated when you want to do numericals. Okay, when you want to do numericals. So I'll just take one small numerical, and then that will help you to solve the problems that are there. It will cover all the aspects of the entire thing. Suppose there is a block of size 1024 bytes. Block can hold 1024 bytes. Let's say the size of a record is 100 bytes. Now I will also write the generic formula here for you to, that will help you. So let's say the block size is capital N. Let's say the record size is, so I'll call it NB to say size of the block, and I will say NR size of a record. Okay. Can you tell me how many records you can store in a block? How many records can you store in a block? What will be the formula? The block contains 1024 bytes. Record contains 100 bytes. Each record contains 100 bytes. How many records can you store in a block? Hold on. You answer the left one. Right one will look later. Answer the left one. Left one, there is a number written, right? 102400. What is that answer? How many of you answered 10.24? How many of you answered 10? Can you store 0.24 of a byte? Is it possible to store it in a PC? 0.24 of a record? You can't do that. That's not allowed, sir. So you can store 10 records per block, and the technical jargon for it is called blocking factor. It's a technical jargon. Okay, don't be afraid. And so what is the formula for this? Is it just NB by NR, or can I say it is floor of NB by NR? It is floor of NB by NR. Clear? Blocking factor? Okay. Let's say that the number of records that are present in the file contains 30,000 records. Okay. How many number of blocks are present in the main file? Each block can hold how many records? You only calculate it. Tell me the answer. Each block can hold how many records? You only calculated, right? Each block can hold how many records? 10. There are 30,000 records in total in the file. So how many blocks will be there in the main file? Can you answer this? I have not even started indexing yet. I'm not even discussing about index file. I'm only talking about uh, main file. Index file अभी मैं गया ही नहीं है. I haven't gone there till now, right? So how many blocks will be there in the main file? Vishnu answers 3000. Everyone agrees to Vishnu or some other answer? Anyone has? How many blocks will be there in the main file? 3000, which is, what is the formula? The formula is again floor of n, number of records in the main file divided by the blocking factor. Clear? Clear, everyone? I have not gone to the index file yet. Okay, I'm just giving you logic here. Rohit says yes. Vishnu says clear. Jigya, how about you? Any confusion? Mohammed, any confusion? See, there are less people in today's lecture, so I will pinpoint people now. So please don't mind. Okay. So let's say the main file is sorted. How many number of block accesses will you do if the main file was sorted? What is the value? What is the number of block accesses, time complexity? If the main file is sorted, if you want to do number of block accesses, so what I'm trying to ask is number of block accesses if the main file is sorted. What will you answer? Which algorithm can you apply? Linear or binary search? Which algorithm can you apply? Binary search. So how many number of block accesses will you do in the sorted case? Order of what? Log n. What is n? N is the number of blocks. If you want to find the number of block accesses, it's log n. No, not plus one. Am I gone to the index file? Have I gone to the index file now? Then why is the plus one coming? That's where many people make a mistake, right? Don't make this mistake now. I've not gone to the index file. Right? When I go, then I will talk. I'm just talking about the main file. If you get the block, you certainly get the record as well. The record, though, it's very easy to search. I'm not even considering the time complexity to search for a record because there is only 10 records per block. Come on here, 10 records per block is very easy to search. You don't even have to study time complexity for it. So if the main file is sorted, you need log of 3000 accesses on average. That's why it's called big O. Big O is average case, right? So that is sorted. If the data is unsorted, how many number of block accesses will I do in the worst case? Sorry, big O is worst case, right? Sorry. So how many number of block accesses will I do if the main file is sorted, unsorted? Which algorithm will I apply? Binary or linear? Linear. What is the time complexity of linear? Order of n. How many block accesses will you do in worst case? 3000. Is this clear? Okay. Okay. Really doing this very well. Okay. Let's say I will just shorten this up. Okay. Okay. Shorten this out. And yeah. Now comes the index file to the field. So now when I consider the index file, I need to know the size of each index record. So record size for index file is, let's say, 15 bytes. Okay. Each record in the index file contains 15 bytes. Is it clear by now that why is it not 100? Is this part clear till by now? It cannot be 100 because you are not storing the entire record in the index. You are only storing the anchor attribute. Is it clear, this part till now? Why is 15 bytes? Why not 100? Okay, perfect. Now, can you calculate the blocking factor for the index file? It will certainly change, right? Because this record size changed. So, what is the blocking factor for the index file? Can you quickly calculate and tell me the answer? Or even give the formula. You don't have to actually tell me the number. Just tell me what by what. That's enough. Because wo to kar hi loge, like you will do that calculation. I'm not worried of if you can do division. I should know whether you are able to do what you have to divide. 1024 by 15. You will take the floor or ceiling. Floor. So blocking factor is you take the floor of 1024 by 15, and the answer will come as 68. The formula is same. The record size only changed. So I'm not writing the formula again. Okay. Okay. Now, let's say that I am using primary indexing. So if I'm using primary indexing, am I storing an index record for every record in the main file? So number of entries in the index file, will it be the number of records or the number of blocks of the main file? What is it? Am I storing an index record for every block? Is it a sparse indexing or a dense indexing? Forgotten by now. Shall I open the slide? Okay. Now answer. How many entries will be there in the index file for primary indexing? Number of blocks in the main file. It's written, right? Come on, you know how to read. So, how many blocks are there in the main file? How many blocks are there in the main file? 3000. So, number of entries in the index file will be 3000. So, how much time? And an index file is always sorted. You understood that by now, right? Should not repeat that thing, right? Index file is always sorted by the anchor attribute. Even if the main file is unsorted, doesn't matter. Index file is always sorted. So how many number of accesses will I do in the index file? It's like there is an index file. This index file consists of 3000 entries. This is sorted. You want to search for an entry in the index file. How much time will it take? How much accesses will it take for you? Which algorithm will you apply? Binary search or linear search? Binary search. So what will be the answer? Number of accesses will be log of what? Log of 3k, because there are 3000 entries in the index file, right? It will be log of 3000. Is this enough? Is the index file giving me the record only? Or does it give me the block pointer? To access the block pointer, I need one more access. Okay, clear? Suppose this is a secondary index. For a secondary index case, the number of entries in the index file will be 3000 or something else. Are you storing an index for every record or every block? It's written in the slide. Number of entries for secondary indexing is number of records. How many number of records are there in the main file? 30,000. Now, can you tell me how many number of accesses will you have to do? Remember, index file is always sorted, boss. Okay. Index file is always sorted. Don't make that mistake. Okay. Correct. Log of 30,000 plus 1. I made a small mistake. I will correct it in some time. Okay. I will correct it in some time. For primary index, secondary index is correct. Give me some time. Okay. I'll correct it. Don't worry. So for secondary index, what will be the number of accesses? Log of 30k plus 1. Is it better than the case where I had? Is it better than the case where I had the main file only? You guys understood this, right? I'm exceeding annotation, so I will have to erase some part. Is this better than the previous case if I were not using index file? For example, if I was not using index file, the unsorted case, I will have to do linear search on 3000 blocks. Number of block accesses will be 3000. Now I have to do log of 30k plus 1. Log of 30k plus 1 is much lesser than 3000. You can do the calculation, it will be much less. Okay. Now there is a small mistake I did in primary indexing. Okay. The number of entries is wrong because how many number of records are there? 30,000. Each block can hold how many records? Is it still 10? Will it be still 10? What is it? Each block storing how many records? Each block stores how many records? 68, right? For the index file, each block can store 68 records. So the number of entries will be 30,000 by 68, which is 45. I made this small mistake. Sorry about that. It will be 30,000 by 68, which is 45. Understood this part? This happens if you rush things. So sorry. Log base 2 of 45. Okay. Small mistake I made. Excuse me for that. Sorry about it. Okay. So, but I hope you are not confused. And is there any confusion? Is there any questions you have regarding this slide? Yeah, I mean, if you do 30,000 by 68, what do you get? Let me do this on a calculator. I had the answer already. 30,000 by 68. What is it? 440. Sorry. Okay. Sorry. I don't know. Sorry. 440. Perfect. Okay. Thanks. That means you guys are understanding. Good. So it's 441. This is a problem actually. 441. Yeah. So this is less than the idea should be, even if the main file was sorted using the index, it was easier compared to access a block compared to just using the main file, because that is log of 3000. This is log of 441 plus 1, which is very less. Okay. Any questions? No, I know I screwed up sometime later, but if there is any questions, I can clear it up. No issues. Okay. Okay, perfect. Now this is the GATE 2021 question, and try this out. Okay, so how many number of records are there? 1,50,000. What is the block size of a record? 4096 bytes. Okay, data file is sorted on the primary key roll number. Very important point. The data file is sorted on the primary key roll number. The size of a record pointer for this disk is 7 bytes. So the size of the record pointer size, which is the pointer to the record, is 7 bytes. Each student record has a candidate key attribute called enum of size 12 bytes. Okay. Suppose an index file consists of two fields, the enum value and the record pointer. So the index file is created on the value enum, and the second part contains the record pointer. Now, can you answer this? Is the trick part here. That's why this is a very good question they have asked. See, is the file sorted on enum? That's why many people will do a mistake here. I'm sure. Is the file sorted on enum? Read the question. No, the file is not sorted on enum, which means, can I say that the main file is unsorted? Because you are creating the index on the attribute which is for which it is unsorted. So the database, that is the file that is contained, if sorted by row number, but you are maybe over smart, you thought I will use the candidate key enum. Now this enum is unsorted. That does not make the data sorted, right? You make the index on the value. The assumption is you will make the index on the value that is sorted. Okay, perfect. If you understood this, very good. Now, suppose a student record is built and stored on the same disk. Assume that the records of data file and index file are not split across disk. This you have to ignore. The number of blocks in the index file will be what? Which type of indexing am I talking about if the main file is unsorted? Secondary. So index record size will be what? What will be the size of an index record? 12 bytes is taken by the candidate key. 7 bytes is taken by the record pointer. In total, it is 19 bytes. Okay. Okay. So far, so good. Okay. Okay. Perfect. 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 So far, so good, right? Okay. Now they are asking the number of blocks in the index file is what? So for that, you have to find something called the blocking factor. What is the blocking factor for the index file? Can you calculate the blocking factor for the index file? Each block contains 4096 bytes. Each index record contains 19 bytes. How many records are present in a block? Hmm. 215. Why there is a question mark? Be confident. 215. Now they are not asking number of entries in the index block. They are asking number of blocks in the index file. So what is the number of blocks in the index file? How many records are there in the main file? There are 1,50,000 records in the main file. and each block can contain 215 records. In total, there are how much? 698 blocks in the index file. Answer is 698. Okay, is it clear? If you do the math, you will get 697 point something. So you can't store point of a block. Fractional block is not stored. You can't store it. So it will be 698. Okay, it was a simple question. I mean, it's not a lot of questions, right? Okay. What else? A file is organized so that the ordering of the data records is the same as or close to the ordering of the data entries in some index. What is that index called? The main thing you have to look at is this. This also means that the data entries can repeat. So there is an ordering, and the index data entries are such that in the main file, those entries can repeat. That's why it's close to the ordering. What is the type of index called? It's called clustered indexing. Perfect. Don't say a question mark. See, it will be wrong or right. It's absolutely correct. It's clustered indexing. Good. Yeah, my iPad for some reason lost connections to Mac, connections to the AirPods. So okay. A clustered index is defined on the fields which are of type. Mohammed says option A. Others agree with Mohammed or some other answer? Option A, right? Clustered index you create on a non-key and the file is sorted. So ordering. You may try this out on your own. If you have any questions, please let me know. Okay. Uh, okay, this is a very interesting question. It's a very interesting question. Okay. And actually, this question is not in your syllabus only. Sorry. I don't know why I added because multi-level indexing, there is only B tree and B plus tree, which we will do that in whatever time we have left. Okay. So you can ignore this question. This question is very good. It's a pattern based question. You have to look at pattern to try to solve the question. And says there is a file which contains the values this 13254. Which one of the following fields is the index actually built from? It's a very good question. Let me know offline if you are able to find the pattern. If you search on internet, you will get the pattern anyway. So it's a very good question. Okay. For instance, just try to look at occupation. The answer is occupation. Okay. But still try to look at occupation and see if you can kind of see this pattern. Does everyone here know about lexicographic ordering? If you were to sort in a dictionary type of thing, right? Now you might have got the answer, right? This is the first record if you do lexicographic ordering. Lexicographic, like if you store it in a dictionary, if you store these words in a dictionary, which word will come first? Which word would come first? On. This is one. Then which word will come? 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 See, that's the values they are stored. 13254, 13254. Okay, it's a very good question. I mean, just pattern matching. Okay, let's use some whatever time is left to look at the tree. So small concept only, so I don't have to worry that there's only 10 minutes left. So we'll take that much only. Okay. So everyone knows what is a BST here. You have studied this in your data structures. Everyone knows BST. So in a BST, if you let's say have a BST like this, it's a very small BST. Let me draw 5, 20. How many values can you store in a node? A. How many values can you store in a node? In a node, how many values can you store? I'm not saying how many children does it have, does a node have. How many values can you store in a node? Just one, right? So one value per node. How many children does a BST node have? How many children does a BST node have? Two children per node, right? Nothing sounds Latin to you till now. It's simple, right? Very basic BST. Now let's say I allow more than one node to be stored in a more than one value stored in a node. For example, let's say I store things like this: 10, 20. A node contains two values. So this left branch will contain all those values which are less than 10. This middle branch will contain all those values that are between 10 and 20. And this right branch will contain all those values that are greater than 20. Is it clear? So far, so good with the structure? Okay. Now, can I say that if there are n values per node, how many children are there per node at max? If there was one value here on BST, so there were two children. There are two values here, so there will be three children. So can I say it is m equal to n plus 1 children per node? Is this fine so far? Okay. Okay. So these type of trees are also called m-way search trees. So there are m different ways where a node can go to search for a particular value. It can either go here, or it can go here, or it can go here. There are m ways it can go to search for a value in a tree. So it's called m-way search tree. Search tree because you are following the rule of BST that a node that is present in the left child is less, the value is less than the parent. Node present in the right child, value is greater than the parent. Okay, so far so good. All is just DSA till now. Even this topic is DSA only. I'm teaching you DSA today. Okay. Now there are some direct questions that people ask that if a node contains three values, what is the maximum number of children that the node can have? What will be your answer? 4, right? So simple now, right? Okay. Okay. Now these B tree and B plus trees are typically used when you want to do something called multi-level indexing. Multi-level indexing meaning if you have an index file which is very big, huge index file, and you want to add another level to it, you do something called multi-level indexing. And typically how you try to store the node is you have, let's say this is one of the nodes of the B tree or M-way search tree. You have the key, let's say key 1, first key value. There will be a child pointer, okay, and there will be another child pointer from here. So these are child pointers. Similarly, there will be key 2 where you will have a child pointer. There will be key 3 where you will have another child pointer like this. Okay, these are child pointers. So you store the anchor attribute keys like this. Now, if you see, I have drawn something here in between. There's another bar. These actually point to the record. This is the record pointer. So the same index file that I had stored, as a linear list where there is a key followed by record pointer, I store them in a tree like this, which is the key is K1. Then I store the record pointer, then the child pointer, which points to the child of K1. Like this I store. So is the node clear? How to store the node? There is a key, there is a record pointer. There is a key, there is a record pointer. Okay. We'll look into an example as well that will make things clearer. Okay. So there are some guidelines that you need to follow in order to draw a B tree. Some guidelines you have to follow. The first guideline that you have to follow is that each node should have at least m by 2 children. And what is m? M is the the number of children. So each node must have m by 2 values must be present. Sorry, I told wrong. So what I meant was each node should at least have m by 2 values present before you try to create a new node. I will explain that later on what I mean by it, but please hold on till now. There is an exception to this above rule, which is root can have minimum 2 children, which is how many values can it have minimum? It can have only one value, it's okay. So for the root, this condition is relaxed. Okay. And the third condition is that all leaf nodes should be at the same level. I might exceed the time today by some 5-10 minutes, so excuse me for that, but it will help you to clear this concept as well. Okay. So there are some guidelines we have to follow when trying to create a B tree. Now let's try to draw a B tree for some set of values that I write here. 10, 20, 40, 50, 60, 70. So here, is it fine if I exceed by 5-10 minutes today? Worst case 10 minutes. So, okay, so I'm saying we have 80, 35, and we want to insert these values into a B tree. Let's say that the B tree value of m is 4. So there are 4 children per node in the B tree. One second, my iPad is disconnecting, connecting, disconnecting, connecting. Now it will be stable. Okay. So each node contains 4 children. What I do here is I first insert the value 10 here. Okay. Then I insert the value 20 here, then I insert the value 40 here. So if the value of m is 4, can you tell how many values can I put at max in a node? If the value of m is 4, how many values can I put in a single node? M is 4 meaning number of children. How many values can I put per node? If you ever forget this later on, you all remember binary tree. Binary tree has the value of m as how many maximum child can you store in a binary? 2. So how many number of nodes are possible, values are possible in a node? Just one, right? Ever try to forget this? You can remember the binary tree, it will remind you. So for if the value of m is 4, maximum number of values I can have in a node is 3. Okay. So this is a node. These are the values 10, 20, 40. Okay. So far so good. So far so good, everyone. Okay. Let's say I try to insert 50. Now, does it violate the condition that the maximum number of values in a node should be 3? I'm trying to put the value as 4. What I will do is I will have to split it. And how should I split it? Draw a line. Okay. Now, whatever is to the left of the line becomes your left child. This value goes up to the root. And the right child is whatever comes after that, which is 50. Is it clear how you split it? Draw a line. Whatever comes to the left of the line becomes a left child. Whatever comes to the immediate right of the line becomes the root, goes to the parent, sorry. And whatever comes after that goes to the right child. Okay? So far so good? Okay. Now I insert 60. No condition is violated, right? It's all okay. I insert 70. Now when I try to insert 80, I'm violating the condition that each node should have maximum 3 values, but in this case it has 4 values. I split. Okay, I split, and what happens? My left child is unchanged. Okay, now what happens here is this 50, so this 70 gets promoted to the parent. So the parent now becomes 40, 70. The 80 comes as a right child of 70. And can you tell where will I put the 50, 60? Middle, or the left child of 70. Okay, all fine till now? All with me? Okay, perfect, perfect. Now, if I insert 35, where will I insert 35? 35 is less than 40, so I go here. And then I can insert 35 here. Left of 40, very good. Is it clear how to draw a B tree? And just to give you one more example, let's say there was 25 that you have to insert. Where will you insert 25? you will insert 25 over here. So this becomes what happened to the 10, 10, 20, 25, 35. Have I violated the B tree condition? I did. So I have to promote this to the parent. So my parent becomes 25, 40, 70. And what will be the left child of 25? The left child of 25 will contain these two nodes. The child between 25 and 40 will contain these two nodes. The child between 40 and 70 consists of 50, 60, and 80 is here. Okay, fine. Understood till now? No doubts, no questions, nothing. Okay, I feel proud of myself that I could teach B tree in 10 minutes. Okay, anyways, okay, let's not go there. Okay, let's not deviate from the point. Now, the last and the foremost thing that I want to talk about is in a B tree, each of these indexes that I have stored are stored as index followed by the pointer to that record, 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 pointer to that record. Like this we store. 25 is repeated twice. Sorry. I should have repeated it. Sorry. Thank you. Thank you. Sorry, sir. I think Jigya, you had the same question, right? Thank you. Sorry, I made a small error, right? So in a B tree, each of these records will have, each of these indexes values will be present in a record. And the record pointer will be present just after the index key. Okay, so this is a B tree. Okay, this is a B tree. Okay, this is a B tree. Now, in a B plus tree, there's only one small change I do. It's a small change I do. In B plus tree, the record pointers I will only store in the leaf node. The record pointers I will only store in the leaf nodes. Okay, you will have a question very soon. Okay, I know there will be a question very soon that, for example, the leaf node here only contains 35. What about 25? Right? You might be having this question, right? Why 25 kahan gaya? Like 25, if I'm not storing the record pointer of 25, how will I get the record corresponding to 25? It's a valid question. Perfect. So I'll go to that. Wait. So 50, 60, they have their record pointers. 80 also has their record pointer. 80 also has a record pointer. Okay. Okay. Nothing I've changed. I've just added the record pointer to the leaves. But what happens to 25, 40, and 70? I am saying you can't store the record pointer here. So what will you do? What you will do is just the mistake that I did a few minutes back. That is not a mistake. I was thinking about B plus tree. You will repeat the value 25 here, and the pointer record will be stored like this. It will be repeated. Similarly, for 40, you will repeat it here, and you will store the record as 40. 70 के लिए you will repeat it here. I don't have space, but I hope you get the idea, right? I hope you get the idea. I'll just write it a bit tougher. So for 70, यहाँ पे what you do is you replicate 7t here, 8t, and then you store the record pointer. So what am I doing here? I am only storing the record pointer in the leaf nodes. And what you do here, you have to also join these two. So this is also called range query. We will learn that later. But this is called range query, where you, if you join it, you can do a range comparison as well. You don't have to worry about it. Just join all the leaf nodes. This is a B plus tree. That's the only difference. Okay? Here, everyone? Okay. I feel proud of myself that I could teach B tree and B plus tree in so less time. So again, sorry if you did not understood. If you still have questions, feel free to ask me offline. There's no issue with it. Okay. Chalo. Let's go ahead and quickly do some questions and then we'll end the class. So I know I have told 10 minutes, but still it's more. So again, sorry for that. I don't want to exceed time, but you know, right? I'm actually going out 20 seconds, so I don't have time after today. Okay. In a B plus tree, the requirement that a node should have at least 50% occupancy is relaxed for which one of the following cases? If you remember what I wrote in the guidelines, you will be able to answer. There is only one node for which that n by 2 condition is relaxed. Which is that node? Shall I go back to the guideline? The m by 2 value should be present per node, but this is relaxed for the root node. So the answer is, what is the answer? Answer is option A. Next question is this, with reference to the B plus tree index of order 1 shown below, order 1 shown below, the order 1 meaning that each node can have maximum 2 values. So uh, that's what it is. Okay, don't be confused. That's what it is. So each node can have maximum 2 values. Order 1 shown below, the minimum number of nodes that must be fetched in order to satisfy the following query. Get all records with a search key greater than or equal to 7 and less than 15. Okay, so see, get all records with a search key greater than or equal to 7. So you have to go this way, right? Less than 15 meaning you will have to go this way. Okay, okay, you have to go this way. Greater than or equal to 7. Sorry, I told wrong. Sorry, 7 is less than 9, right? So greater than or equal to 7 meaning you go this way. So you search for 7 first, then you go this way. This is one node you access. This is the second node you access. This is the third node. Sorry, what am I doing? So this is the one node you access. This is the second node you access. Third node you access. Fourth node you access. Less than 15 meaning you will stop here. Okay, so how many nodes are you accessing in total? 4 nodes. Good, very good. I think I repeated the question, sorry. Consider B plus tree in which the maximum number of keys in a node is 5. What is the minimum number of keys in any non-root node? Come on, answer. So if you are allowing maximum number of keys as 5, what is the value of m, number of children? 6 or 4? Let's see if you are not confused. 6 or 4? Again, remember binary tree. Maximum number of keys is 1. So children is 2. Maximum number of keys is 5. Children is 6. What is the minimum number of keys you can have in any non-root node? M by 2 is what? M by 2 is 4 or 3? What is ceiling of M by 2? 3. Option C is the right answer. Okay, so I think we had done almost in time. Sorry. Okay, let's not joke about it. Sorry again, I've exceeded time a bit. Again, a quick overview of the entire subject. Last week's question. Did I miss any? Okay. Acha, that conflict equivalent wala na? Okay. Sorry, I don't have time, and I forgot about that absolutely. Okay. Uh, Let me do one thing. Okay, I will share the solution on the WhatsApp group to you guys. Is that okay? There's no next class. Okay. Sorry about it. There's no next class. I will share it in the WhatsApp group. If you have questions, feel free to ask. I missed that. Sorry. Okay. Anyways, yeah. Thanks for reminding me. I absolutely forgot about it. Okay. Fine. Uh, sure. Let's. Okay. So what I was saying is there's an quick overview of things. We looked at ER diagram. We looked at relational model, relational algebra, relational calculus, SQL, transactions. Again, my still I would suggest you guys, if you have not studied DBMS till now, if you are underconfident of DBMS, please do not enter the exam hall without knowing normalization, functional dependency, and normalization. Anyway, normalization, if you write, functional dependency is a prerequisite, so just normalization should be enough. This is the utmost important topic in your exam. And if you have time, please look at indexing because it is easy. It's an easy topic. And if you have time, look at ER diagram. That's enough. Relational algebra, relational calculus. I'm not saying you to leave. I'm saying if you have less time, you can choose to skip it. Skip it. Because you have to focus on other subjects as well. Okay? These are the, I call, most important topics, MIT. Uh, Let me share the slides on the chat window. Thank you for joining. Again, apologize for the time being exceeded. I will stop the recording.